Suppose that you needed to know the length of a curve on some interval. We know how to do that for straight line segments, but curves are trickier. However, it turns out that we can use techniques similar to the ones we've used for areas and volumes in order to compute this length. Because we know about straight line segment lengths, we can approximate our region using a series of straight line segments. We can calculate the width of each of those and use those to get more and more accurate estimates of the length of the curve itself. Our plan is going to be to divide the region up into smaller and smaller sections, draw a segment connecting endpoints of each of those segments on the graph, use the distance formula to find the length of each of those segments, and then add all of those up to get an approximate length for our curve. Let's take a look at this plan a step at a time. Here we have some graph, some function, maybe f of x, and we wish to know its length on the interval between a and b. So what we'll do first is divide that region up into smaller sections. Next, we'll draw a segment on the graph that connects the points on the graph that begin and end on the subsections we just drew. This is going to give us a series of straight line segments, each of which we can calculate the length of. Now we'll use the distance formula to find the length of each of these segments. We'll pick one to represent how we would do it for each of these. First thing we need to do is identify the endpoints of our segment. The left endpoint, we'll call that c sub I as its x-coordinate, which makes its y-coordinate f of c sub I. The right endpoint, we've changed x by a small amount, which we'll call delta x. So that point is c sub I plus delta x, f of c sub I plus delta x. Now that we have two x coordinates and two y coordinates, we can use the distance formula to calculate the length of that segment. The length is going to be given by the square root of the difference in the y-coordinates squared plus the difference in the x-coordinates squared. So this looks like f of c sub I plus delta x minus f of c sub I all squared plus c sub I plus delta x minus c sub I squared. We can tidy that up a little. Not much happens in the first part. We still have f of c sub I plus delta x minus f of c sub I all squared, but the second part just becomes delta x squared. We're going to simplify the length of that segment in some ways that will be helpful to us. It's a little bit of a trick, but what we're going to do is factor out an x squared. In order to do that, that means we have to multiply the first term by delta x squared over delta x squared, so that when we factor it out, we are left with f of c sub I plus delta x minus f of c sub I squared all over delta x squared, and then plus 1 for the second term. The first term in our sum then contains a square on the top and a square on the bottom. We can bring that square to the outside. So now we have f of c sub I plus delta x minus f of c sub I all over delta x, and that entire quantity is squared, plus 1. Because the delta x squared is under the square root, we can pull a delta x outside, leaving us with the square root of f of c sub I plus delta x minus f of c sub I all over delta x all squared plus 1. The formula we found represents the length of one of the many segments we constructed on our curve. We're going to now add them up to get an approximation of our total length. That's going to be represented by the sum from I equals 1 to n of the square root of f of c sub I plus delta x minus f of c sub I all over delta x all squared plus 1 times delta x. Now we do a little calculus. The mean value theorem tells us that for a continuous differentiable function on an interval a to b, there is always some point on that interval where the derivative is equal to the slope of the secant line. The quantity in the parentheses under our square root represents the slope of the secant line connecting our two endpoints. Therefore, the mean value theorem tells us that there is some value, we'll call it k sub I, that lies in the interval between c sub I and c sub I plus delta x, where that quantity is exactly equal to f prime of k sub I. This tells us that we can rewrite the total length as approximately equal to the sum from I equals 1 to n of the square root of 1 plus f prime of k sub I all squared. We know that as we let n go to infinity, this type of sum turns into an integral, and so we see that our total length is going to be the limit as n goes to infinity of this sum from I equals 1 to n of the square root of 1 plus f prime of k sub I all squared, and that is going to be equal to the integral from a to b, the region over which we wanted to know the length, of the square root of 1 plus f prime of x dx. We can write that using dx dy notation as the integral from a to b of the square root of 1 plus dy dx squared. So we see that if we have a continuous and differentiable function on some interval ab, and that function is of the form y equals f of x, then the length of the segment connecting a f of a to b f of b is going to be given by the formula L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. We can use similar reasoning to come up with a way to construct the arc length of a function that is in terms of y. So if x is equal to g of y and it's continuous with a continuous derivative on the interval c to d, then the length of the segment connecting g of c, comma c to g of d, comma d is going to be given by the integral from c to d of the square root of 1 plus g prime of y squared dy. Let's try using this formula by computing the arc length of the graph of y equals 3 ln x minus x squared over 24 on the interval from 1 to 6. The region we're trying to find the length of is highlighted on the graph shown on the screen. Our function is y equals 3 ln x minus x squared over 24. We're going to need to take the derivative of this. So dy dx is going to be 3 over x minus x over 12. If we square that, we're going to end up with 3 over x minus 1/2 plus x squared over 144. We know then that our length must be the integral from 1 to 6 of the square root of 1 plus dy dx squared dx. So if we add 1 to dy dx squared, the negative 1/2 becomes a positive 1/2, and we get 9 over x squared plus 1/2 plus x squared over 144. This is a perfect square trinomial, which means it factors. It factors as 3 over x plus x over 12, all squared. Adding that to our integral, we get that the length is the integral from 1 to 6 of the square root of 3 over x plus x over 12, all squared, dx. The square root and the square, because we're dealing with positive x values, will cancel each other out, and we end up with the integral from 1 to 6 of 3 over x plus x over 12 dx. Given that we know the length is the integral from 1 to 6 of 3 over x plus x over 12 dx, we can find antiderivatives. The antiderivative of this function is 3 ln x plus x squared over 24. We'll evaluate that from 1 to 6. And that's going to give us 3 ln 6 plus 36 over 24 minus 3 ln 1 minus 1 over 24. The natural log of 1 is 0, so we get 3 ln 6 plus 35 over 24 as our final answer. If we want to approximate that, it's approximately 6.834 units. Let's take a look at another example. This time we'll examine x as a function of y. We've got the function x equals y squared over 8 minus the natural log of y, and we're looking for the length of that on the interval from 1 to 10. We'll take derivatives with respect to y this time. So dx dy is going to be equal to y over 4 minus 1 over y. Squaring that, dx dy squared is going to give us y squared over 16 minus 1/2 plus 1 over y squared. We know that our length is the integral from 1 to 10 of the square root of 1 plus dx dy all squared with respect to y. Adding 1 to dx dy squared gives us y squared over 16 plus 1/2 plus 1 over y squared. As in our previous example, this is a perfect square trinomial, and it factors as y over 4 plus 1 over y squared. Because all of our y values are positive on the interval in question, we can write our integral without the square root and without the squared, so we get that the length is the integral from 1 to 10 of y over 4 plus 1 over y dy. Taking antiderivatives, we get y squared over 8 plus the natural log of y from 1 to 10, which is 100 over 8 plus the natural log of 10, minus 1/8 minus the natural log of 1. The natural log of 1 is 0, so we get 99 over 8 plus the natural log of 10. Summarizing what we've learned, when we have functions that have continuous derivatives over some interval, then we can calculate the length of the curve on that interval by using the integral from a to b of the square root of 1 plus f prime of x squared dx when y is a function of x, or the integral from c to d of the square root of 1 plus g prime of y squared dy when x is a function of y.